no AI system, no physical AI system can actually go into an unknown, unmapped environment and navigate it and make a cup of tea. We also have a bigger team now than we had back then. And so it's opened up a lot more possibilities. But the very fixed, kind of simple and boring approach is what we tried before. The remarkable thing, though, was indeed that for many cultures, the majority, even as our results showed, they were able to reorganize their activity. There were caveats to that. If you had the culture was too uneven or they were just dead all on one side, that broke down. But we represented all of this data in the paper. Um, but yeah, so there was a lot there.
Yeah. So how specific do these starting conditions need to be, or is it really the beauty of these biological systems is that provided the right inputs, they will self-organize into a functional larger system? Does that sort of always happen, or are there loads of situations where your starting situation wasn't right enough, the sensory neurons weren't set up in the right way, connected to the motor neurons, and then it just didn't learn the game? Explain sort of how robust the system is in response in with that initial starting conditions and the inputs from the game itself.
Yeah, very big question there, and one we've been doing a lot of work on. In fact, a very recent paper that's not out now, but will be out by the time this episode airs for sure,
Cool.
has spent a lot of time looking at this question. How does the structure and the function relate? What setup leads to the best performance? And so, as you'll be able to see in this work, we actually have the case where we've done all sorts of things like Morse code classification, MNIST, which is a type of handwritten digit task that people use in machine learning often. And we find really strongly that the structure that you set these cell cultures up in have a very strong effect in how they're actually able to perform certain tasks. But it varies, and some tasks benefit from some structure more than others. So there's a lot of complexity here and a lot of nuance, but that also means there's a lot of control in how we build these systems. And this goes all the way back to that point I made before is we're not necessarily trying to build a human brain in a ditch. We're trying to figure out how do we build, how do we bioengineer the best type of cell culture, the best material to achieve the goals we want to achieve. And I'll give you like an example is that bees are far simpler than a human. And yet bees are remarkable in what they do and in many things they do, humans could not achieve. And so again, why, we don't need to make more humans. There's plenty of humans out there who are looking for work to do. Let's do that. Let's figure out how to do something totally different.
I find this so unbelievably cool. So how much inspiration are you able to take from what we know about the architecture of the human brain and the type of problem and task that that part of the brain is equipped to solve? How well are you able to replicate that system in your monolayer multi-electrode array, and how informative is that? Can you take a particular brain region, we know it's good at doing this task, like language, like Broca's area, for example, something like that. Does that map onto the type of problems that your monolayer neuron system is then able to, is it better equipped to solve?
Yeah. I should clarify as well that we don't just do monolayers. That's what we did in
Okay.
the initial Pong work. But we do all range these things called organoids, which are a little more spherical and they're meant to be sort of a mini organ, but they're far simpler than brains. It's not quite right to call them a mini brain because they don't have that complexity or connections or the diversity of cell types, but they do have a lot more complexity, at least geometrically, than a uh, a monolayer. And then we also do these bioengineered modular units, which kind of move further from physiology, but still have some really unique properties. Uh, in terms of how much do we take inspiration from the human brain specifically, quite a lot. I mean, the team, my background is in neuroscience. We have several other neuroscientists on the team. And so it would certainly natural, I guess, pun intended, to take inspiration from the thing itself, right? And so if we want to look at things like, let's say, the hippocampus, which famously has these very powerful place coding cells, would be silly not to take what we know about that when we go and develop hippocampal cells, which we've got and done, and we've got a paper out on that at the moment. Um, but there's a big difference from taking inspiration from something and trying to copy it exactly. And so we don't throw away what evolution and physiology has done. That would be insane. But we also aren't going to try to recreate it, which I think has a similar degree, recreate it exactly for those purposes, at least anytime soon, uh, until we had some sort of evidence or justification to do so. Because that would also similarly be incredibly technically difficult.
Yeah. Very cool. So, talk about the process. If you have a new task or problem that you want the neural system to solve, say MNIS or any of the other tasks, what would be the process by which you start to think about or try to start model the type of architecture that might be optimized for that system as a starting place? Like, how do you think about that process?
There's thinking what I can talk about right now. There'll be some exciting stuff coming out soon, but I can't talk about it right now. Sorry,
You
sorry,
can
Evan.
you can talk about it
Uh,
right now, Brett. You can. You can.
what I'd say is cautiously that there's there's a lot of different approaches, and actually, there's far more that we don't even know that we don't know still about this space. And so, a lot of our work needs to be from ground principles, exploratory. We sometimes take inspiration from machine learning, which is kind of closing the cycle because a lot of machine learning was inspired by neuroscience. So now we sometimes take inspiration from that. For example, like on like reservoir computing approaches and other things that people might have heard of. Um, there's a whole range of things. Sometimes we do take inspiration from, again, the physiological basis. So we might say, well, actually, bee brains have this type of connectivity. So we want to try and achieve this type of connectivity. But a lot of the time, it just comes down to good old fashioned science. You try something, it works, or normally it doesn't work. You try something else, you write it down, you move to the next thing. Where we've sort of reached an unlock is not necessarily that we are so much more clever than any other lab out there. Uh, and there are many labs out there who are doing good work that also we can be informed by. Of course, that may, to me, it goes without saying, but I should say it actually. There is a lot of amazing work being done, and we collaborate with a lot of amazing scientists all around the world. But where we have a particular advantage is that we have, as I said, server racks of these units. So we can actually iterate and run through thousands of hours or more a week just to try and find the answer to a question that previously would have taken labs years to do. Take, for example, this Doom game, right? Again, that was built by someone who's a non-expert in the field in about a week or so. It took us something like 18 months to really get a Pong environment working to a similar degree of control, I would say. And that's because we had to start all the way from the ground floor. Don't get me wrong, that was a huge engineering challenge. And Andy Kitchen, who did the substantive of that work, did an amazing job in building it. But he started with very little, right? It all had to be built from the ground up. That's so slow. When you've got the foundations that we've laid, you can move much quicker.
It's so cool. What maybe give a few other examples of tasks that you have been able to get good, very good or good outputs from. Like what other things can these systems do right now?
Yeah, so we've been looking at a few things. Some of the ones I can talk about are things like this handwritten digit classification, seeing if cells can identify the 0 to 9 digits, which has been really exciting. Morse code has been fun. Um, can neurons
Explain that.
decode?
Elaborate on exactly teaching it Morse code, what that means exactly.
Well,
You're having a
the reason,
conversation
yeah,
with this thing?
yeah. The way we started out initially was we kind of did what we refer to sometimes internally as a Y maze test. Y maze is a really classic neuroscience test. You put the rodent normally. People have built bigger ones for I think dogs and monkeys and other things, but normally it's rodents. And it's literally just a Y-shaped maze, and the rodent has to choose to go left or right. And we would sort of drop in a stimulation either on the left or the right. And we just wanted to see would the cells respond very differently to this, and would they respond in a way that would kind of align. So we were kind of doing this spatial classification, and we wanted to move on to a rate-based classification. And so we were thinking, well, how's the best way to do that? And I realized, well, there is already a rate-based classification. It's called Morse code. So why invent our own rate-based classification when we could just say to people, we're going to try Morse code because that already exists and it's essentially the same thing. And what we found is actually cells are really sensitive to rate coding. So we found that Morse code is a very strong effect. Cells are pretty good at it. Um,
Love it. Love when guests bring up the giant shoulder as well. Fantastic reference. Really, really appreciate it. How sophisticated a game can these systems play, do you think? Have you got a chess bot out there? I mean, like, I think that I would feel very inadequate if I lost a game of chess to 800 neurons in a dish. But can
chess,
it play
yeah.
more sophisticated games where the mapping, like, this is really high level strategy, lots of playing down different routes, and like the game, to model the game, you just need like a really complex data structure, right? And like, LLM and like AI systems will destroy any human chess player now, will destroy any Go player. I don't know if there is actually a game that exists that AI can't beat humans in, but I'm like, how do you think that maps to your kind of systems? Could you get a
The-
really good
yeah.
AI or a really good cortical chess system?
There are games, but, and this is interesting things. And there's this Moravec's paradox. Have you heard of this?
I've heard it mentioned, but please refresh.
So essentially, this states that things that computers find easy, humans find hard. Things
Right.
humans find easy, computers find hard. So if I was to do the square root of like 10,025, 0.892 in my head, like I can't do that in my head. I'm going to get bored. It'll take me a long time to do with a pen and paper. Uh, but a calculator, very simple, can do it immediately, right? Because it's a deterministic system. But likewise, no AI system, no physical AI system can actually go into an unknown, unmapped environment and navigate it and make a cup of tea. If you put a robot in my house and you say, go make a cup of tea, it's not doing that without shattering most of my cups, if ever, right? It requires, but you could do it, right?
I'd
You'd go
like
to
to
other
think
people's
so.
houses, you would guess, you would figure it out. So it's actually, something like chess. Why is chess such an interesting thing? Because it's really hard for humans to do it perfectly. So we have competitions. Who's better at a really hard thing? But computers are quite good at it. Games that computers find hard, for example, like first-person shooters with incomplete information. If you give the perfect game world, to the computer, it can be pretty good, right? But you don't get a perfect information environment when you play a first-person shooter, right? Especially not against other humans. Uh, so these are the sorts of things. So we're not aiming to build a system that is going to compete with what computers are good at. We're aiming to build a system to augment what computers are bad at. And so it's things with real-time changes, with fuzzy information, with dynamic real-time or limited information, things that biology has to learn to be very good at. When we evolved and we saw a tiger or a lion in the grass, we weren't able to sample 10,000 times. Is that a lion? Is a lion going to eat me? We had to make the decision, right? Oh, well, Fred got eaten by the lion last time, so let's get out of here. Like that's how we have to evolve to learn. And so biology still has these properties. The question isn't, and I think this is the beautiful thing about it, the question is not, is it possible for brain cells to show intelligence? When we're looking at machine learning, the question is it possible for silicon to show general intelligence? We don't know, right? We do not know if that's possible yet. Current attempts, despite trillions of investment, have not done it. But we know for biology it is possible. The question is, how do you get it? And that is a powerful question, I think, to begin this work. And it's really what led us to begin this work in the first place.
Yeah. It's really well said, and I appreciate what you mean, but I'm still curious if you think you could do it. So say Cortical Labs
Yes.
they're pivoting tomorrow, right? Your entire job is to now make a chess cortical system. And Magnus Carlsen's coming in. He's helping you as much as you want. Like, you have infinite money. Like, do you think that the best
Yeah,
cortical chess system could beat the
yeah. Well,
best chess AI system? I think that's a really interesting question, even if that's not your mission.
probably not, right? That's kind of what I was getting at before, because the current machine learning AI systems, whatever you want to call them, uh, can play the game essentially perfectly, right? And so humans can't do it. So probably the answer is no. Um, we'd be looking to solve different problems. Now, there are hybrid approaches that could get quite interesting, and we are interested in those. But in that case, it's not a purely biological system. So,
Yeah.
do I think there's huge capabilities in what people call heterogeneous compute? Yes. I think heterogeneous compute or hybrid computing is incredibly interesting. But a pure biological system, no. No, humans can't do it. I don't think we're going to be building anything that's better at these sorts of things uh, in any time soon on their own. But could we augment an AI system to give it something that's even better? Very possibly, right?
Yes.
Um, and Cortical Labs, of course, looks at these heterogeneous systems as well, a little more in our research arm. So we do take a lot of different approaches there. And I think the future of computing is headed that way, heterogeneous compute, not just GPU and CPU, but your biological unit, your quantum unit, your neuromorphic chip, figuring out how to use the various tools in our toolkit the best way possible, right tool for the right job.
Yes. Yeah, I guess I was curious, do neurons in a dish, do they exhibit the same sort of scaling properties as LLMs, where you just keep getting this better performance the more you cram in? Like if we did build trillions upon trillions of neuron systems, how much better can those systems be? Do you think or do you know, do they exhibit a sort of similar scaling law to LLMs? Is it just different when it's biological intelligence? Do you have any thoughts on that?
Different is probably the right word. Uh, if you consider bees again, like I like bees, so go back to bees a lot. Consider bees. Bees are pretty small, 800-ish, 200 to 800,000 cells, depending the bee you're talking about. Probably there's more variability than that, but it's roughly that range. Uh, Yet they navigate their environment pretty well. They can find things from a good long distance for relative, especially relative to the bee. Uh, they can do pretty complicated stuff. They build. It's remarkable what bees do. But then consider an elephant, right? Elephants have much larger brains than humans. Does the elephant navigate its environment that much better than the bee, given that it has so many magnitudes more cells? No. So the scaling isn't the same. And if it was, we would see humans with bigger brains be that much smarter. And that's just not the case, right?
Yes.
So So I think like the answer to that is like it's going to be different. A lot of it depends on the structure. We've actually moved to smaller cultures than what we did back in the early prototype days. We used to use about 800,000 to a million cells. Now we've gone back down to about 200,000 as our standard setup. And we get better results, more controllable results because it's better specified.
Interesting.
So I think there is a story there about growth, but I don't think it's nearly as straightforward as bigger is better.
Right. Like I was very interesting. I was curious, do you get a better Doom player if you just like linearly as you add more neurons? It's just not that simple. It's not how
No,
biological
no,
intelligence works.
it's certainly not the case. The complexity and structure matters a lot. It's unfortunately not as straightforward a story as that. If
Yes.
only it was the case, because growing bigger cells is not the hardest shit. We throw away most of the cells we ever make because we don't have don't have things to put them on. Um, if all we had to do was grow 100 billion cells and suddenly we'd have a device that was so much better, my job would be very easy. Um, unfortunately, uh, unfortunately, there's a lot more complexity there, but it's that very complexity which makes this such a beautiful and promising approach.
Yes. So how do you think about the future of these heterogeneous machines? Will there be neurons in my Mac 7? Or do you know what I mean? Like where will we see this in the world? How exactly will the biological systems interact with the AI that's being built at the moment? How do you think about that in the future?
Yeah, look, you know what they say: predictions are hard, especially when they're about the future. Um, the Do I think that we'll have biological neurons in like sort of consumer laptops anytime soon? Probably not. I don't. But cloud use for certain tasks and applications, a lot, especially with the use of new, sort of frontier models and all that today. A lot of processing you might use your laptop to do isn't actually done on your laptop. Um, a lot of the Like for my laptop, most of my stuff is stored in the cloud. I bring it down into my laptop when I need it, right? A lot of the processing for some of the most complicated things we do is done off my laptop. So might that be a use case for your computers relatively soon? Yeah. I mean, if you logged on to the Cortical Cloud, you could do it today, albeit, we're just at the start of the journey, but you could do at least some of it in a very, very basic, rudimentary, experimental sense right now. So I think that's possible. Um, but I think there are other types of devices other than laptops, edge devices, for example, where some of the properties of neural systems, like the very low power, very high sample efficiency, in other words, doesn't need much data to learn, becomes very promising.
Interesting. Can you give an example of that?
So I think things like edge robotics are particularly promising. We've often used robots as an example because, again, you have a ground truth that we are essentially neat robots walking around the world doing all right. We seldom crash into things, sometimes, but seldom. Uh, and so we know kind of like, yeah, controlling an entity in the real world is a thing biological cells can do quite well. So we think robots is a super interesting example, and physical AI is receiving a lot of attention at the moment. But the truth is there's a reason these results haven't really bridged into the dynamic worlds just yet on their own.
The Giant Shoulder mission is to explore radical ideas in biology, neuroscience, and consciousness, and elevate those stories to the highest possible level while keeping them accessible to everyone. If this interests you and you want to support independent science, then please consider subscribing to the Clips channel